Today we are performing a new topology optimization tutorial with Nastran Solution 200. My name is Christian and I'll be helping you through this exercise. This one's very different from traditional topology optimization. Usually you're trying to minimize the compliance quantity or you're trying to increase or maximize the stiffness of your structure. This example is going to walk you through how to minimize the mass or weight while constraining for both stress and displacement constraints. So by the end of the video, this is what you can expect. We're going to start with this solid part that starts off with the mass of 18 kilograms, and we're going to end with the lighter mass of 9.3 kilograms. Again, we're going to impose both stress and displacement constraints. Now, just a quick summary of what we're going to do in this example. We're going to start off with our original design. We're going to have this topology solution, and you can see often topology solutions are very rough looking. This then requires a step of refining the design and performing a subsequent verification analysis to make sure that this final design has met your design requirements. So here, quick summary of the structural model. At the holes, we are constraining the holes. These two holes at the bottom that you can see, we are constraining them. And then here at this top hole, we are applying our force in different directions. So this will require the use of two different subcases or two different load cases. Here in the top right, you can see the units we'll be using for this example. And now a quick summary regarding the optimization problem statement. Here, I should have been a little bit more careful, but I believe there's also a section here that's P solid 2. So let's go ahead and actually step back out of this. Let's open Patran and see what we have here. In the last picture, it looked like there was only one P solid 1, but let's go ahead and see how many actual P solids there are. Here I'm just doing some manipulation so we can see these color coordinated. Okay, so we actually have a P solid 1 and P solid 2. If you want to confirm what P solid numbers you have, go to properties and property name plot and select all the properties you see here. Here you can see that these actually are using the same names as you have defined here, but we need the ID numbers of these actual P solids. So in order to do this, once you have your BDF file, go ahead and import it. And before you import, select MSC Nastran input options and unmark this checkbox that says retrieve names from comments. This is going to import the properties as ID numbers, and you'll see in a moment what I mean. Also, click on create property groups. We'll go ahead and click OK. After we selected the file here, we'll click apply. So number one, this wasn't the example, but I'll use it anyways. If you click on the model tree, you'll see that groups have been imported here. Let's go ahead and show some of these groups. So this was the checkbox that said on import create groups. So we'll go ahead and select these two groups here. So here you can see that we have two P solids here. Let's go ahead and actually display what their names are. And here we go. So here we now know that this red region is P solid 1 and the holes are P solid 2. So here know that P solid 1, which is the green region, that will be our design region. So we're going to vary some of the elements there. The red region is the non-design region. So here, this image is still accurate, except that we left out P solid 2. The important thing is that P solid 1 will be the design region. So that would be, again, this green region. The red region will not be selected as a design region. Now, what about our objective? We're going to minimize the fractional mass. If you've seen some of my other videos, usually we are trying to minimize the compliance. Recently, there was a new capability in Nastran that allows us to actually perform topology optimization and minimize, or rather set the objective as minimizing the mass. Also new in that Nastran release is the ability to create stress constraints. So we'll apply stress constraints. We will also apply displacement constraints. So here at the load application node 5622, we want to make sure that the vertical deflection is no more than positive 0.0008 meters. And then the stress, we want the bond MSC stress to always be less than, what do we have here? Than the stress specification we have here. So before getting started, just in case you're an engineer, you're new to topology optimization, if you have a comment, you have a question regarding training, you are welcome to contact me at this email address at the screen, and I will get back to you with an answer. Now, today we are going to use the Nastran Solution 200 web app. This is going to let us perform topology optimization. If you're a student or engineer, you can get access to this app by sending me an email. Now, let's go ahead and begin this example. Let me make sure I'm actually using the correct presentation. So let's go ahead and go here. So a quick summary regarding the steps. So the first thing you should start off with is the BDF file. This BDF file is going to be converted to Solution 200. We're going to specify the design region, the objective, and the constraints. We will then perform the optimization. Then we'll look at the results towards the end. One other thing, at the end of the presentation, I'm going to go through some commonly asked questions. If you're a new user to topology optimization, I have a feeling these slides are going to answer many of your questions, so definitely stick around towards the end so I can explain to you these concepts. Now, before we perform this topology optimization, let's discuss the topology optimization workflows. There are two ways that I'm familiar with in performing topology optimization. One method I'll call the traditional method. This involves setting the objective to minimizing the compliance. This is sort of counterintuitive. Usually when you optimize, you want to optimize for weight. You want to minimize the weight. But with the traditional approach, it's kind of backwards. The objective is to minimize compliance, whereas the constraint is a fractional mass. So here we are saying that the final mass of the design should be some target. So here, for example, if we set the mass target to 0.75, we're saying that keep 75% of the material. If the design is above 75%, then the design is not valid. With the traditional approach, once you have the topology solution, so here in blue, it's a very rough solution. You then have to go through this procedure of refining the design and then finally performing a final verification analysis to confirm that your quantities such as stress and displacement are within your requirements. Now, there are instances, such as this case here, where you can go through this whole workflow and find out that your final design does not meet your requirements. So this whole solution is invalid. What often happens is you perform multiple topology optimizations, each one with a different fractional mass. You go through the topology solution. You then create a refined design. You then perform a verification. Out of all the designs that are verified and validated, you pick the best one out of all those options. So here we see this option and this option have verified results. So now which one do you pick? The one with a mass of 9 grams or the mass of 7 grams? Of course, this is the one that weighs the least. So this design is the design you would finally select. Today we're performing the latest topology optimization method. The benefit of this method is you can many times avoid the excessive effort that you would with the traditional approach. My recommendation is that you first try both methods. If the traditional method works best for you, then use the traditional method. If the latest method works for your particular application, go forward with this one. But here, the idea is to minimize for weight while simultaneously optimizing for a stress constraint. So this final design is more likely to meet your structural requirements. After you have this topology solution, you still go through the process of refining it, and then at the end, you always confirm it by performing a verification analysis. So this again is the procedure. This is the workflow we are using today. So let's go through the process. If you want to follow along, from the homepage of the web app, if you go to the user's guide, to the topology tutorials, this is the example we are working with. Feel free to download the file and follow along with this video. So now that the PDF file is on my desktop, we can start the tutorial. So the first step of the conversion process, remember, we want to take this PDF file. It may have come from your post processor, such as this one. We want to convert it to solution 200. So to do this, click on the middle icon for topology optimization, then upload the file to the web app. The web app is going to identify all the regions that can be set as design variables. And here you can see that it's saying I can set psolid 1, 3, and 2 as design variables. As I mentioned a moment ago, there's a special way to import your model. So instead of displaying the names, so here it'd probably be a worth exercise to show you the names again. So here we'll go ahead and click this. You notice here it says this is solids and this is solid supports, but here it says psolid 1, 3, and 2. The special option to import the model will give you those identification numbers that you need to use. So here psolid 1 and 2. So here I know that this red region is actually psolid 1, and the blue region, which is the non-designed region, is psolid 2. So that would be here in blue. So here what I need to select is psolid 1. In the next table, you see that psolid 1 is now design region X1. This completes the creation of the design variables, but I should also mention this is where you can specify the von Mises stress constraint. So here if you click under options, mark the checkbox for show stress limit column. This is where you can specify what the upper bound for your von Mises stress is. And here, let me just go back here and look at my optimization problem statement. Here I see that it's 2E8. So let's go ahead and type that in, 2E8. And here it's set here. And so remember, this, with the traditional approach, you can rarely ever put a stress constraint, but here is a special option to specify the von Mises stress constraint. Once we're done with this, we can move on and configure our objective. Let's go ahead and delete this default compliance objective, and let's go ahead and look for fractional mass. We'll go ahead and set this as the objective, and we'll go ahead and set it as minimized. Next, we'll go ahead and create our constraints. Here, we're going to delete the default constraint of fractional mass, and we're going to create a displacement constraint. So let's go ahead and search the list for displacement. I'll go ahead and say that the Z component, or the T3 component for grid 5622 should always be less than 0.008 meters. And now what's left to do? You'll notice that we just went through the process of specifying our design region, our objective and constraints. We just stated our optimization problem statement in Nastran terms. You'll notice that as we created the design variable or region, it created the Nastran entry for us. As we created the objective, it created that Nastran entry for us. Next, we can go to settings and make one modification. The maximum number of design cycles. Here, 50 wasn't enough when I tested this. If you set the maximum number to design cycles of 100, you'll find that this example will converge around 70 design cycles. After you're done here, let's go to the exporter and download this entire converted BDF file. Here, if you notice, the BDF file is contained in a package. This package includes an auto execute program. So if you double click this, it will start the optimization. And notice these two new BDF files, model and design model. These are the same ones here and the same ones here on the right. Basically, it's the same BDF file as before, except solution 101 is now solution 200. And all the statements for the regions, the objective, the constraints, everything else is included in the design model BDF file. At this point, it's performing the optimization, so it's a good time to go over some additional slides, but I think I just went over those. It'd be worth mentioning these again. Remember, there are a few ways to perform topology optimization. There's the traditional approach, where you minimize the compliance, i.e. you maximize stiffness. For constraint, you specify a fractional mass, so you're saying that the final design has to be less than 0.7. So here it'd probably be 70%. Or you could specify 0.4, which would be 40% target mass. We're using the latest topology optimization method. This involves minimizing the mass, so you're trying to minimize the weight, and we can apply a stress constraint. If you're wondering which method you should use, I recommend testing both of them for your application. Each method works a little differently for each application. In some cases, the traditional method works best. In other methods or applications, the latest method works best. In this tutorial, I'm going to get you to the point where we get to the topology solution. Prior to this video, I went ahead and refined the design the best I could in the few time I had. And then I'm going to show you the verification. But again, this step here where I go from the topology solution and refine design, this I'll leave it up to you to do some other time. So let's go ahead and check where the optimization is at. And currently we are, let's see if this is running. Yes, this is running. If you don't see an update here after a few moments, another way you can check if it's running or not, if you open the F06 file, you scroll through it, you'll find these sections called design cycle. So here we're currently at design cycle 28. I expect this to finish around design cycle 70 if everything went through correctly. So at this point, I'll just go ahead and pause the video here, and I'll just continue the video once we're ready to go. Actually, this is a good time to go through some of the slides in the appendix. So the slides I promised to cover at the end, this is a perfect time to go through these slides. I know for new users, these will be very helpful. So the first question I get asked a lot, what is fractional mass? Here, let's suppose the initial design is 6 grams and the final design is 1.8 grams. Here, the fractional mass compared to the initial design is 0.3 here. So fractional mass just means how much of the original mass is still there. If it's 0.3, that means 30% of the mass was kept. If it's a 0.4, that means 40% of the mass was kept, and so on and so on. One comment regarding, or here actually it's not necessary, I cover that. The next question I get asked commonly, what are the design variables in topology optimization? Let's suppose this entire structure had one density, 1,000 kilograms per meter cubed. During topology optimization, each element will be given its own density. Here I'll say a density or rho I. The design variables in this case are normalized material densities. So here let's just randomly pick one element and say that the normalized density, rho n, is equal to 0.5. If the normalized material density is 0.5, what is its actual density for this design cycle? Here, it's rho I divided by the original density. So we know that the density of this element is 500 kilograms per meter cubed, and underneath would be the original density. So here we know this element has 500, a density of 500. What if it's 0.6? Here it would be 1,000, and then on top you would have 600. So the optimizer will vary these normalized material densities. These are the design variables. So by the end, you're going to have a spectrum of values. So any design variable or normalized density that's close to 1, that is indication that that is a very important element that should be kept in the final design. Normalized material densities that are close to 0 are elements that could potentially be ignored from the final solution. Here in white, you can see which elements are not necessary. And the other thing to note, during the topology optimization, elements are never removed from the model. They're always kept. Instead, you're given a ranking system where you can determine which elements are critical and which elements are not. So here, everything in white is close to 0. Everything in red is close to 1. So using this method, you can determine which elements could be removed and which ones can be left. So here's just another way of looking at these normalized material densities. Here you can see each normalized material density has about the same size. So this is representing that they're equivalent normalized material densities. But here again, it's going to vary the size or the value of the normalized material densities. The size might get so small where you can already tell that these elements are not necessary for the final solution. One last thing. Remember what I said, that in topology optimization, none of the elements are ever removed. All of the elements still exist in the solution. Instead, you're giving this ranking system of normalized material densities. In order to remove these elements and see what the actual ideal solution is, there is a step where you need to specify a threshold. So here in the right-hand column, you see this threshold value. What is this threshold column? So here we see a plot of normalized material densities, and here we see the range of values. Here at the top we see 1, and at the bottom we have 0 essentially. The threshold means find 0.3, and any element with a normalized material density greater than 0.3, you're going to keep. Everything below that threshold is going to be left out. So here on the image on the left, this is what the solution looks like after applying this threshold. And now I can actually step out of the PowerPoint and look at some results. So here we have the final message, run terminated due to hard convergence. Here the green checkbox indicates that the optimization has gone through successfully. You can see it took about 70 design cycles to minimize the fractional mass from 0.9 to a new fractional mass of 0.24. Here we know that we started off with the 90% mass reduction, and at the end, it ended up at a result that is about 24% of the mass of the original part. So here, let's go ahead and minimize this and now look at some results in our post-processor. So in the directory where the optimization was performed, there is a DES file. This file contains all of the normalized material densities, all of the final ones at least, that I mentioned a few moments ago. Remember, values that are close to 1 indicate you should keep that element. Values that are close to 0 are elements that you could probably leave out. So to import this file here and to look at it, do as follows. Go to Tools, Design Study, Post-Process, select Result File, Downloads, and just navigate to the directory. Click OK and Apply. So here, Patron will go ahead and bring them those results. Now let's go ahead and display these results. We'll go ahead and select this case. I think the threshold was 0.3. Go ahead and confirm 0.3. Remember, this threshold is going to keep elements that are greater than normalized material density of 0.3. So here you go. This is the topology solution from this optimization run. You can see it's very rough. This is definitely not something that you should consider the final optimization solution. You then have to go through this process of refining this design. So here as an example is what the process will look like. After you have the topology solution, use your processor to refine the design. I personally like using MSC Apex. That really makes it easy to add voids, add features, manipulate my initial design so I can quickly get this refined version. It also makes it easy to perform this last verification step. In this video, I won't show you this process of constructing the refined design. I will show you this final verification step. So let's go ahead and open the second file. And one thing I did not do is I did not run those results. So here is the refined design. If I spent more time, I could have done a better job, but here I did what I could in the short amount of time. You can see these corners are very what's the word I'm looking for? Acute. These are definitely going to cause high stress concentrations for this next verification step, but I figure in the interest of time, I'll still go ahead and evaluate this as is. So let's go ahead and see what the results are for this refined design. Remember, we're looking for a von Mises stress no greater than 200 megapascals. So that would be 2e or 2 times 10 to the 8. So let's go ahead and look at some results. In this case, we have 2 subcases. So let's go ahead and look at the first subcase.